Okay, so again, control the fluid level H to some desired level HD in some tank. Okay, designing a specific closed loop control U. In open loop, like I said, you just turn on and off a tab and you watch and measure HD. If you want to do this automatically, and this is what the toilet input is doing, okay? The toilet basin, the toilet tank is doing that. Okay, the toilet tank is a simple level control. Okay, controls the level of the water in the tank. Okay, we do a simple control so that the tank doesn't spill over. Okay, that's what the toilet does. Toilet tank. I'm not joking. This is for real. Just watch it. It's a simple mechanical controller. Right. So the initial level is H0. Okay, good. What's the dynamics of this tank? You know, a more complicated tank, so more design. Okay, a different kind of model. Okay, essentially the fluid level you have in the toilet. If you want to do a simple control, you linearize it in open loop, just like we learned. You do a simple linearization around some equilibrium point, and then you do a linear controller based on that. And you see it's working, okay? Your toilets do not spill over. Okay, so the dynamics has this is fully nonlinear. You have this square root function here. H is the state. Please note that this is a scalar system with a single state and a single input, single output system with a single command control U and a single output H, a single measure output H. So you see, this is nonlinear. AH is the cross section of the tank, so it depends on the level, and A is the cross section of the outlet pipe. That's constant because the pipe is constant. But the cross section of the tank depends on the level, as you can see here, because it makes sense. Depending on the level of the fluid, you compute a specific cross section. So how do you linearize that? Not in the sense of taking very small variations. You want a full linear dynamics. Please note that this is not local in the sense of very small variation. Feedback linearization is more of a global linearization technique because it's not talking in this, at least up to a certain point, it's not taking into account the equilibrium points, as you can see. So you want to have a linear part. So essentially, you need to cancel out this term. So how do you cancel out this term? You just pick A to be plus A square root GH. But that's not enough. You need to add something because this needs to be a system. You add an input depending. Oh, and you also want to cancel out this guy. Okay, you want to cancel out this guy. So you take this input. You also add this input. So this one plus this one. Okay, and finally, in closed loop, you get this very simple integrator system. Okay, this is an integrator. We know that. Yeah. You realize that, yeah? Because you can take Laplace on this one and you get SH S, or let's use small, not capital letters, is VS. Okay, so essentially, if you do then the transfer function H of S, which is the output HS over V of S, okay, this is 1 over S. So this is an integrator indeed. Okay. Choose the equivalent input V is minus alpha H tilde, where H tilde is the error. So you can pick this. And alpha is a constant positive. So the closed loop dynamics is this guy. And this is stable, so this goes to 0 as t goes to infinity, because alpha is positive, so you get here h dot is my h dot tilde. I think this they forgot some tilde here. They wanted to do this. Is minus alpha h tilde. Alpha is positive, so this is stable. So the error goes to 0 as t goes to infinity. Okay. What's the command law? So this is the command you're trying to use. This is the command you're trying to use. Okay. This term provides, the first term is the output flow, and the second term raises the fluid level according to the desired linear dynamics. Okay. They say here, if the desired level is also time varying, because you need not necessarily ask for a constant level, but a time varying level, then the input V, it has this form, and it's still stable. It's still stable. Okay, so this is a simple example of the power of the feedback linearization technique. Okay, this is how you want to do it. It says here, canceling the nonlinearities and imposing a desired linear dynamics can be simply applied to a class of nonlinear systems, in so-called companion form or controllability canonical form. Yes, because this is totally controllable. That's why you could pick a very simple U to cancel the nonlinearity. Controllability is a powerful tool this time, and please, when you study this back home, please go back to the linear systems theory, either from the dimension reduction course or any other materials you can check out, and check out again controllability. This is very important, and observability, okay? Because they are very much related, and feedback linearization is relying on these very, very powerful properties, okay? So controllability is essential. That's why you could pick this U, because this system is controllable. You see, U acts on all the terms automatically. So this H depends directly on U. So that means H is controllable through U. And the whole system is controllable because the system is a scalar. But what happens when this is not the case? And this is in the so-called controllable canonical form. I do remind you, oh, I have no space to write here because I can't use the bloody OneNote. I would need the space of the stupid OneNote. It's still not loading. I think there is a problem. I think there is a problem with OneNote. You people are right. But I didn't have this problem this morning, if you ask me. This is new. What I'm trying to say is controller canonical form. This is a controller canonical form. Okay. For instance, for a linear system. This means that all the equations are x1 is x2, x2 dot is x3, and so on. And finally, xn minus 1 dot is xn, and xn dot is a bunch of equations. Okay, usually in the linear case, a polynomial like of the previous states. Okay, so it's minus an xn minus and so on and so forth minus a0x, something like that. Plus, and here is u. This is the controller canonical form. You can see that in linear systems theory. Okay, so a system in companion form or canonical form, x and x. This is this means n times differentiated in time. This notation. If it's in this form, u is a scalar control input, x is the scalar output. Okay, and you make the notation x, bold X is this with all these differentiations up to n minus 1. This is the state vector. Fx and Bx are nonlinear functions of the state. Okay? There is no derivative of the input u. This can be presented in this controller canonical form. This controller canonical form. Okay. X1 is X2, just what I said here. This you know from the linear systems theory. Okay. Linear. In linear, it goes to this form with a polynomial, where this guy here is a polynomial in the linear case. Okay. For non-zero B, it says here, define the control input U equal 1 over B times V minus F. Because you want to cancel the nonlinearity. Just do this. Substitute U here, and in the final equation, you get X and dot equals V. If you pick this control. This is what you get if you substitute this U in here. And then the control law of this form, V, okay, you pick this V. Ki is chosen such that the roots of this polynomial are strictly in the left half plane. Of course, you want this to be stable. So this polynomial needs to be a Hurwitz polynomial. Okay, this is a Hurwitz polynomial. Okay, this is a Hurwitz polynomial. Hence, this equation, I don't know what ES means, exponentially stable. That's what it means. This is exponentially stable. Okay, because you require because of this or due to this requirement of having this polynomial Hurwitz. Okay, all right. Okay, and you also get exponentially convergent tracking of this form. Okay, right. They say here this method is extendable when the scalar x is replaced by a vector and the scalar b by an invertible square matrix. Of course, you can do this in more variables as well. Okay, so you replace u by an invertible function of this form. Okay, an invertible function of this form, and you do get your linear system in closed loop. There is another example here. The example of a feedback of a two-link robot. The example of a two-link robot. Each joint equipped with a motor for providing input torque, it says here, an encoder so you need to measure the joint position, joint velocity, the objective, the joint position Q1 and Q2, Q1 here, and Q2 here, follow desired position history. So they need to follow specific positions, okay, because you want to manipulate this arm. For example, when a robot manipulator is required to move along a specified path, for example, to draw circles. So these positions help you achieve a specific goal. So this is the problem, the control problem we need to solve. We need to sort out. You realize that this robot link, this is described by a nonlinear model. I think this is more than clear because we are talking about rotation motion, and which includes, from the pendulum, as we know, it's including a series of nonlinearities we need to deal with. Okay, and now, for instance, it's showing here a way to model this robot link, this robot arm, a way to model this. Okay, so we are using Lagrangian mechanical modeling, okay, which is this one. Okay, these equations where Q1 and Q2 are the position, the joint angles, tau1 and tau2 are the joint inputs, and the functions h11, h12, h21, and so on are of this form. Very complicated. You see here the cosine, okay, and here another cosine, and cosine of Q1, okay. So it's not so easy, as you can see. So control law for tracking. Okay, control law for tracking, computed torque. So this is the law we pick to cancel the nonlinearities, as you can see here. Okay, as you can see here. All right, where V has this form, and Q tilde is the position tracking error, and lambda is the position constant. Okay, and Q tilde satisfies this second order differential equation, okay, with Q tilde converging to 0, because as you can see here, the polynomial, if you take this in Laplace, this linear second order equation, if you take the Laplace transform of this equation, you get a second order polynomial with all the coefficients, with all the constant coefficients in positive. Hence, this is going to yield a Hurwitz polynomial. So this is a stable. So you see, this is one way to compute a control law to achieve feedback linearization and stability. Okay, but this is because the systems have rather simple models, even if they are nonlinear. Please keep this in mind. The question is, the idea is, or the question is, how do you give a general procedure to achieve feedback linearization? And now we get into the details of this. We have input to state linearization. And the nonlinear dynamics is not in the controllability canonical form, because many of them are not. We need to use coordinate transformations. Okay, we have the single input, single output system, general nonlinear system, x dot is fxu. And the input state linearization technique is like this. Find the state transformation z is dx, and an input transformation u is ux, such that the nonlinear system dynamics is transformed. So through this procedure of getting an input that cancels the nonlinearities, we need to compute a coordinate transformation. Okay, a coordinate transformation which brings the system into a linear form. Okay, and then once you have this new control, okay, you apply the linear techniques. E.g. Kalman controller, Kalman filter. Okay, so this is essentially the procedure we want to develop. Example, we have this nonlinear system, as you can see here. Okay, nonlinearity, nonlinearity, nonlinearity. The equilibrium point of this guy is the origin, apparently. It's probably the origin. Okay. I guess so. This is 0, and if this is 0, then you get this equation, x2 cos x1 is u cos twice x1. 0, of course, is a solution, and apparently it should be the only one. The nonlinearity, you see, this time you cannot directly cancel the nonlinearity. U is not showing up in the first equation, if you have a look. Okay, it's not showing in the first equation. So you need to define a new set of variables. You need to do a coordinate transformation. For instance, z1 is x1, z2 is ax2 plus sine x1, which is this part. Okay, z1 dot is minus 2z1 plus z2. How come? z1 dot is x1 dot. So it's minus 2z1 from this term plus z2. Look how we chose z2. Look at this guy. Indeed, so the first equation is right. The second equation, x2 dot, x2 dot. So z2, look, then you get Z2 dot is AX2 dot plus X1 dot cosine X1. Okay. And X1 dot is this guy. Okay. So the second equation is a bit more complicated. That's what I'm trying to say. The second equation is a bit more complicated. The first equation is linear, if you see. The second equation is this one, which is a bit more complicated, but it's not very difficult to see because here you just substitute the things. Okay, so this is Z1 dot anyway. Okay, Z1 dot, and you substitute it from the first equation. X1 is Z1. Okay, look here. X2 dot is this guy, and if you manipulate in the second equation of X2 dot, you can get everything in Z coordinates. So you get this system. You have the same equilibrium at 0, 0. That's not changing because this is a coordinate transformation. Coordinate transformation is just changing the geometry, is not changing the equilibrium points. And now, because you have this in some sort of, let's say, some controller, some canonical form, here it's easy to pick the control law. It's easy to pick the control law. Essentially, you pick U, everything that's canceling the second equation, plus an additional term. In the new dynamics, this is what you get. So if you substitute U into this guy, if you substitute U here, and you can do that, you have a lot of simplifications and a lot of canceling of terms. And finally, you get this very simple system. By a proper choice of feedback gains K1 and K2, so you can replace this by a state feedback, and you can place the poles of this system wherever you like. Both Z1 and Z2 converge to 0 because this is a stable system. This is a stable system. Hence, also the original state is actually stable. It's very interesting, this coordinate transformation and this control input, so also a coordinate transformation on the input, if you like, they help us also assess stability, but not in the first approximation sense, but in a clear system sense, in a more or less. You see what I mean? It's not the same as looking at the linearized system. The linearized system is a different object. The linear system obtained here in closed loop, this is not a different object. This is the same object, okay, of the same type, or same type with a nonlinear system, okay. However, the result is not global. The result is not global. And also the result, they say here, is not valid when X is in this, when XL, who's XL? I don't know who XL is. Okay, I don't know what XL is, but they say apparently for some values of X that this is not valid. The input to state linearization is achieved by a combination of a state transformation and an input transformation. So you don't do like I said, I was right. You don't do just a coordinate transformation on the state, but also on the input. It's state feedback in both. To implement the control law, they claim that the new states Z1, Z2 must be available. If they are not physically meaningful or measurable, they should be computed by measurable original state X. If there is uncertainty in the model, it says here, okay, it should be also reflected in the new coordinates in the control input U. For tracking control, the desired motion needs to be expressed in terms of the new state vector. So if you want to do tracking now, you have to compute everything in the model in the new coordinates. Two questions they say here arise from more generalizations, which will be answered in the next lecture. In this lecture, what classes of nonlinear systems can be? This is a good question. So how for which classes of system is the feedback linearization responding, and how to find proper transformation for those that do accept feedback linearization. Let's have a short break and let's discuss and see what the slides reveal after the break. Okay, sorry, I'm back. Sorry for the long break, although I hope it has been quite helpful for you. Right. Good. So the last questions we were discussing were what classes of nonlinear systems we can apply this type of coordinate transformations to achieve feedback linearization, and how can we compute the transformations. This is another important question because you need to compute these coordinate transformations. Input-output linearization. So we consider this system, x dot is fxu and y is hx. The objective is to track a desired trajectory, y desired. Okay. So y needs to follow a specific shape. Okay. This is y desired, and you want y to come and follow somehow this shape. This is y. Okay. yd and its time derivatives up to a sufficiently high order are known and bounded. So this is important information, okay, about the behavior of the desired output and its derivatives. This is really, really important. The difficulty, so the output y is only indirectly related to the input u. It's not easy to see how the input u can be designed to control the tracking behavior of the output y. Okay, at least I think this is this is like an open loop discussion. Okay, so you have to be able to do that in closed loop, to design a procedure to do this in closed loop. Okay, all right. So what's the approach? The approach is this so-called input-output linearization. You generate a linear input-output relation and you get a controller based on linear control techniques. This is the idea, actually. This is the main idea behind everything in feedback linearization. You'd like to linearize or get a linear form of your dynamics so that you can apply linear control techniques. And here we have an example. We have this third order example. You have three equations, nonlinear equations. You have polynomials and the sine function as weak nonlinearities, as we call them at the beginning of the lecture. And apparently we'd like to control x1 because x1 is measurable. Right. What's some observations, some remarks about this system? So to generate a direct relationship between the output y and the input u, we need to differentiate y. So y dot is x1 dot, and x1 dot is sine x2 plus x2 plus 1 x3. There is no relationship. So what can we do? We differentiate once again. And you'll see that this differentiation is actually related to the zeros of the system in a nonlinear sense. Okay. This is quite interesting. Okay. So actually, what do when you have a transfer function, let's think about this. When you have a transfer function like this, ys over us, and this is a polynomial, okay? So this is bs over as, okay? What are the zeros? You know, zeros mathematically is very easy. The zeros are the roots of the nominator of this function. Okay, so b of zi equal to 0. But what does this actually mean? What does this actually mean? This means that yzi, which is what? Which is bzi uzi over azi. It's what is the value of this function? This is the meaning of a zero, or an input-output transmission zero, transmitting from the input. In this point, the input has no influence actually on the output. So, and the zeros, this is what they actually mean. That at this level, there is no influence on the output. So you have to differentiate once, you have to differentiate twice, that's the second zero. Again, is there a relation now? Yes. And if you differentiate again, you look here, there is a relation. U appears in the second derivative. Okay? In the second, so the zero is sort of like a first order zero, multiplicity one, because at the second level, or zero, yeah, at the second level, this actually, the input has an influence. The input has an influence. There should be a very interesting relation between the zero dynamics and actually, no, between this, this is actually the relative degree. The relative degree is the number of zeros of a transfer function, And you have this complicated formula in F. Okay, this is just computation. So you select a control input. This is the control input you need to select. This is the control input you need to select. Okay, after the second differentiation of the output. Very interesting, okay? Very interesting. You choose then this specific control function. You realize here this is the tracking error, depending on the tracking error, with some positive constant, and you do stabilization. If you do, if you choose stabilizing values for K1 and K2, which we can very easily do, then you know that the tracking error is asymptotically null. Okay, it's asymptotically going to zero. Okay, and then the closed loop system. The closed loop system has this very simple second order form, and you achieve your goal. You get the tracking error going to zero. So you do everything using this input-output stabilization. But to do that, you have to be careful about how many times you differentiate your output. At which derivative, the question is, at which derivative is the output presenting an influence on the output? Very interesting. Okay. If you're talking about dynamical issues, then actually this relative degree and number of zeros and all this and zero dynamics is closely related, as we'll see, to notions such as observability. You remember observability from linear systems when the output, if the output is zero, sorry, if the and the output not being zero when x is not zero. Okay, that's what observability is. I'm just making a negation of the unobservability property. Right. It says here the control law is defined everywhere except at the singularity points such as x2 equal to -1. Yes, it's true. Look at the shape of U. To implement this control law, full state measurement is necessary. Sometimes you haven't got that. It ain't available. You can't just measure the states, because the computation of both the derivative y and the input transformation need the value of x, which is true. If the output of a system should be differentiated r times to generate an explicit relation between y and u, then the system is said to have relative degree r. And this, we'll see this formalized in terms of the Lie derivatives. Okay, you remember that from the other lecture with Romanian slides, Romanian language slides. Okay, so for linear systems, this terminology is expressed as the number of poles minus the number of zeros. This is called the pole zero excess, if you remember. The pole zero excess. Okay, for any controllable system of order n, taking at most n differentiations, the control will appear to any output. Okay, so the relative degree is less than or equal to the dimension of the system. If the control input never appears after more than n differentiation, the system would not be controllable. This is very interesting. So this is another characterization of controllability. So if the relative degree is not less than or equal to the dimension of the system, then the system is not controllable. This is very interesting, isn't it? Feedback linearization, we continue. So internal dynamics, a part of the dynamics which is unobservable in the input-output linearization. Okay, this is called the internal dynamics of the system. In the example, it can be x3 dot is x1 squared plus 1 over x2 plus 1, y differentiated twice, so minus this function. Okay, so this is the internal dynamics of the system. The desired performance of the control based on the reduced order model depends on the stability of the internal dynamics. Okay, and here's an example. Stability, it says in the bounded input, bounded output case. We have this polynomial, very simple polynomial second order system. You note that the second equation is just an integrator. The control objective is for the output y to track a desired trajectory yd. Okay, you differentiate. Y dot is x1 dot. Linear input, and this is linear in the input u. You can realize that. So the control law is very easy. Okay. And you have an exponential convergence, it says here, of the error. This is the error, okay? Y minus yd. What is the internal dynamics? It says here x2 dot plus x3, x2 to the third power is this guy. This is the internal dynamics. Since the error and yd dot yd are bounded, okay, x2 is also bounded. So things are quite all right. Input-output linearization can also be applied to stabilization when you pick the desired tracking, the desired trajectory to be tracked to be 0. Okay, so if you do this, then you achieve stabilization. Okay, so for the previous example, the objective will be y and y dot to be driven to 0, and stable internal dynamics guarantee stability of the whole system. That makes sense. Okay, no restriction to choose physically meaningful h. Okay, you can choose physically meaningful, as it says here, outputs, which is true, and this is correct. Very interesting. You see, it says here, different choices of the output lead to different internal dynamics, which some of them and some of them can be unstable. So this is very much depending on the output you pick. This is very interesting. This is very, very interesting. Okay. When the relative degree of a system is the same as its order, there is no internal dynamics, of course, because you have so the number of poles equals the number of zeros. And then the problem goes back to input to state linearization. So these are a few remarks, very interesting to help us understand what's going on. So essentially, what you need to do for feedback linearization, you set a desired trajectory to be tracked, and then you compute relative degree, you check out the pole zero excess, you look at the internal dynamics, and if you selected your output such that the internal dynamics is stable, then you get a stabilizing controller very easily. That's the main idea to gather from these slides. Okay, so let's sum up part of the things we have discussed so far. Feedback linearization cancels the nonlinearities in a nonlinear system such that the closed loop dynamics is in a linear form. This makes sense. Canceling the nonlinearities and imposing desired linear dynamics can be applied to class of nonlinear system named in companion form. Okay, so for instance, in controller canonical form, okay, or controllability canonical form. We saw that. And essentially, this is what you do with all these procedures to compute stuff. You want to bring your system into some controller canonical form if that's possible, and then you want to compute the feedback linearizing control law. When the nonlinear dynamics is not in a controllability canonical, input state stabilization input to state linearization technique is employed. You transform the input and the state into companion canonical form. That's what you do. Okay, and then you use standard linear techniques to design a controller. For tracking a desired trajectory, when the output y is not directly related to the input to the command or the control u, input-output linearization is applied. Okay, so it's explained here when you use input-output linearization, when you use input-to-state linearization. Okay, and this is rather important. Okay. Formulating a controller based on linear. Okay, relative degree is the number of differentiating y to find an explicit relation to the input, a direct relation to the input u. Okay, this is what the relative degree is, and this is what the relative degree is. Okay, if the relative degree r is different from the dimension n, then we have n minus r internal dynamics, and their stability needs to be checked. That's what it says. So these are a few conclusions of the things we have been discussing so far. Okay. Now let's talk about the internal dynamics of linear systems. So let's apply the concepts we have seen so far a little bit for the particular case of linear systems, because the linear systems are always, or should always be, a particular case of the general theories we developed in systems theory. If linear systems are not a particular case, then you have a problem with your theory. Just trust me, this is always the case. In general, directly determining the stability of the internal dynamics is not easy since it's nonlinear. That makes sense. Non-autonomous and coupled to the external closed-loop dynamics. We are seeking to translate the concept of internal dynamics to the more familiar context of linear systems. Okay, so let's see this linear system. Very simple second-order linear system. The control objective again is to track y with a desired trajectory, to have y follow a desired trajectory yd. Differentiation. You see, since y is the output y is chosen as the first state x1, so we can measure state x1. When you take the derivative, you immediately see that the input is has a direct connection to the first derivative of the output. So the control law is this one, okay, and this is the simple law governing the error, the tracking error. And then the internal dynamics is this one. Yd dot minus E is x2 dot plus x2. Since E and Yd dot are bounded, then x2 and U are also bounded. So things are quite nice. Okay. Now let's take a different dynamics. Let's change the sign in the second equation. Okay, and we use the same, and then this is the internal dynamics, but this is not stable any longer because of this minus. Okay, because of this minus. They are asking why the same tracking design method is yielding different results. And it says because the transfer function of 3 is s plus 1, so you have minimum phase, even if it's unstable in s squared. Okay, both have this, they both have the same poles but different zeros. And the thing is that W1 is very good because it's minimum phase. Okay, whereas W2 is non-minimum phase. So the stability of zeros is extremely important. And if you remember, you have seen this throughout this 4 years of control studies in this faculty, in this department. You have had courses of control engineering, control practice, and so on and so forth. And every time If you remember, even when you did the PID controller is very bad when you have unstable zeros, when you have non-minimum phase. If you remember the loop shaping you studied in the second year, okay, loop shaping, there was a huge problem with non-minimum phase systems. The design, the control design was far, far more complicated, and stabilization is an issue. Just check it out. Just take the simple system S-1 over S+1 and try to stabilize it with a PID and see the problems because of the S-1 0. So non-minimum phase systems are kind of a big problem. Okay, so in general now, we have a third order linear system with 1, 0, it says here. For instance, this is a particular case. Probably the author is trying to have these particular things, not to generalize to far more complicated formulae. This is the transfer function of this system, okay? Because it's a third order system with 1, 0, meaning you have a first order degree polynomial in the nominator and a third order degree polynomial in the denominator. You can very easily transform this into the controller companion form. So this is controllable, yes. This is controller canonical, this form. Yeah, you see here, the 1 here, and this companion form of the matrix. Okay. Okay, so this is companion. It's not unique. Companion of s to the power 3 plus a2s2 plus a1s plus a0, a1 s plus a0. Okay, this matrix. So this is controller canonical form. You know this from the linear systems theory, or you can check this out. Okay. This is control canonical. So if you take the second derivation, because you see here that the relative, the pole 0 excess, E, how should I put this? Excess, EX, okay? The pole 0 excess is 2, because you have 3 poles and 1 0. So you have to differentiate twice. So U appears in the second differentiation, because this is the relative degree, okay? The required number of differentiations, the relative degree, is indeed the same number of poles minus number of zeros. So the pole 0 excess. The input-output relation is independent of the choice of the state variables. 2 differentiations is required for you to appear even if you use 5. Who's 5? Even if you use this. Okay? So it doesn't matter how A and B look like. You see what they mean. You still have relative degree 2. And what is the control law? So the control law is this guy. Okay? And it says here, exponentially stable tracking is guaranteed. The internal dynamics can be described by one state equation. Okay? Z1 can complete the state vector, so on. Okay? So this is a very simple equation of the internal dynamics. Okay, so if y is bounded, then the stability of the internal dynamics depends on the quotient minus b0 over b1, of course, because this is the coefficient of z1 in the second term of the differential equation, and it needs to be b0 over b1 needs to be positive to achieve stability in this case. If the system is minimum phase, it says here, the internal dynamics is also stable. The internal dynamics is also stable, independent of the initial conditions and magnitude of the desired trajectory. So this is that's why we do use. You remember we have been discussing this minimum phase. Why it says that? Because if the phase is minimum, if you remember from the loop shaping theory in the second year, due to Bode theorem, due to the theorem of Bode or Bode's theorem, good phase in the mid-frequency range, because that's where the stability issues appear when you do loop shaping. Okay, due to Bode, a good frequency range is for minimum when the phase is minimal, when the controller does not bring too much phase to destabilize the system. This is the idea. And minimum phase systems have this property. So they are very good for control. That's what it means. Minimum phase systems are very, very good and very useful for control, and much easier to control than non-minimum phase systems. And now we further proceed to the so-called zero dynamics. So this is to characterize the zeros of a system, linear, non-linear, or in particular a linear system. Zero dynamics, it's actually the dynamical description, if you like, of the notions of zeros of a transfer function, okay, which we know from linear systems. This is a dynamical characterization, a state space dynamical characterization of the notion of zeros. For linear system, the stability of the internal dynamics is determined by the locations of the zeros. Okay, so zeros in the open left half plane mean stable internal dynamics, whereas zeros not in the open left half plane create unstable internal dynamics. To extend these results for nonlinear systems, the concept of zero should be modified, it says here. And it's not modified, it's just extended. Okay, it's generalized. I wouldn't use this term if you ask me. Okay, this is too harsh. You don't just modify it, you just extend it to have a meaning for nonlinear systems as well. Extending the notion of zeros to nonlinear systems is not trivial. We're kind of expecting that. Okay, nothing is trivial when you talk about nonlinear systems, if you ask me. In the linear systems, input-output relation is described by transfer function, which is zero with and poles are its fundamental where zeros and poles are its fundamental components, of course, because they are the roots of the numerator and the denominator, zeros, denominator, poles of the transfer function. But in nonlinear systems, we cannot have a transfer function. That's what it says here. Zeros are intrinsic properties of a linear plant. Kind of makes sense. So the zeros of a transfer function, that's what they're trying to say, is a notion which is peculiar to linear systems. You can't just say zeros of a transfer function for nonlinear systems. But for nonlinear systems, the stability of the internal dynamics may depend on the specific control input. So who are the zero dynamics? What do we consider the dynamics of the zeros? Is defined to be the internal dynamics of the system when the system output is kept at zero. Yeah, just remember zeros. YZI is BZI, where ZIs are the zeros, over AZI, UZI, and this, since this is zero, this is zero. So this is how we want to characterize it. You keep the input, you keep the output at zero through an input in the points ZI. That's what zeros are. Okay, the output and all its derivatives at zero. So it's an internal dynamics. This is what the zeros are, an internal dynamics when the output at certain values renders is rendered null by the input. Okay, so for dynamics 2, let's see who number 2 is. This guy. So for this guy. Okay. The zero dynamics is this guy because you had U in this part, so this is zero. We find input U to maintain the system output at zero uniquely. Keep x1 0 in this example. By Lyapunov function v equal x2 squared, it can be shown that this is asymptotically stable. Okay? For the linear system 5, which is this guy, a third order linear system. So for the linear system 5, the zero dynamics is z1 dot plus b0 over b1 z1 is 0. The poles of the zero dynamics are the zeros of the system. This is very important. So who are the zeros of a transfer function, they are the poles of the zero dynamics, and this is very important. The poles of the zero dynamics, this is very important. Okay, now I was trying to make some connections to the research I'm doing, because I'm trying to do model reduction with preservation of zeros, so that the approximation has a good meaning, or keeps a very good meaning of the original system. And I've always been thinking, I can do this for single input, single output systems, but I can't do this for the moment for multiple input, multiple output systems. But this is a way to look at it, because zero dynamics shouldn't be, I'm not sure if this is connected to single input, single output, or you can compute zero dynamics for multiple input, multiple output systems. This is something I have to think about. Very interesting. Okay. For linear systems, if all the zeros are in the left half plane, globally asymptotically stable of the zero dynamics, globally stable of the internal dynamics, I guess this is what it means, gas in GS. Globally asymptotically stable and globally stable. Okay, so in linear dynamics, okay, the zero dynamics is globally asymptotically stable. Okay. In nonlinear systems, no results on the global, so you can do this globally in the nonlinear case. Only local stability is guaranteed for the internal dynamics, of course, even if the zero dynamic is globally exponentially stable. Okay, GES. Okay, so G is globally, E is exponentially, S is stable. Okay. Zero dynamics is an intrinsic feature of a nonlinear system, which does not depend on the choice of the control law, of course, or the desired trajectories, because also when you have a linear system and you have a transfer function, zeros of the transfer functions are the zeros of the transfer functions. It doesn't matter which input you pick. The output matters because the output computes the transfer function, but the input is not relevant in this case, so it doesn't change anything. Examining the stability of zero dynamics is easier than examining the stability of the internal dynamics, but the result is local. That's what it says here. Zero dynamics only involves the internal states. Internal dynamics is coupled to the external dynamics of the desired trajectories. Makes sense. Okay. Right. Similar to the linear case, nonlinear systems whose zero dynamics is asymptotically stable is called an asymptotically minimum phase systems, although you can't talk about phase. Phase is a notional frequency domain of complex numbers and complex functions, complex calculus. Whereas in this case, yeah, but just we do this notation abuse, okay? This is an abuse of language and notation, but this is very good to help us towards the control ideas. If the zero dynamics is unstable, if the zero dynamics is unstable, different control strategies should be sought, of course. A summary control design based on input-output linearization is in 3 steps. Differentiate the output Y until the input U appears. Choose an input U to cancel the nonlinearities and guarantee tracking convergence. And then you study the stability of the internal dynamics. So this is the main procedure for this. If the relative degree associated with the input-output linearization is the same as the order of the system, the nonlinear system is fully linearized, and then you get a satisfactory controller. That's what it says. So if R equals to N. That means when you have no zeros, or you only have zeros at infinity. That's what it means. Okay, if you have functions such as 1 over A of S, that's what it means. You have no zeros. If the relative degree associated with the input-output linearization is the same as the order of, okay. Otherwise, nonlinear system is only partly linearized. Whether or not the control is applicable depends on the stability of the internal dynamics. So when that's actually what the idea in this sentence is that once you have zeros, things get more complicated. That's what it says here. Okay. Right. Now let's have a short break, and then we start to dive in again into some mathematical notions we solved before the holidays. We do a recap and try to understand and see how things evolve in this respect. Okay, break, and I'll see you. I'll see you soon. Okay, I'm back. So mathematics, okay? Preliminary mathematics. Well, you remember the notion of vector field defined on Rn. Smooth vector field, so f has continuous partial derivatives of any required order. So essentially f is continuously differentiable many times, okay? And this renders it a vector field, a smooth vector field. Okay, so the functions essentially they are infinitely many times differentiable and all the derivatives are continuous. The gradient of a smooth scalar function is the row vector denoted by nabla. That's the sign nabla. H is dh dx, okay, where an element j is dh with is dh dxj, so is the derivative of h with respect to the component of the state xj. A vector field admits not a gradient but a Jacobian, as we know from linearization, okay, from simple linearization. Nabla f, also denoted by nabla f, is df dx, where an element nabla f of ij is dfi to dxj. Then we need the lead derivative of h with respect to f. You remember we used that also when we were discussing uh, um, Lyapunov stability. The derivative of h with respect to f is a scalar function defined by LFH. Okay, so derivative of h with respect to f, LFH, is dh dx times f, or nabla h is with the notation used here, times f, where h is a smooth scalar function and f is a smooth vector field. If G is another vector field, then LG LFH is nabla, is the derivative of LFH times G. Okay, so like this is the derivative is like this is so this is DLFH dxG, like this. So we use different notations, okay? Last time we didn't have such a notation with nabla, but here probably for the sake of simplicity, they're using this notation. LF0H is H itself, okay? It's H itself. LFIH is LF of LFI minus 1 H, okay? So we can do this I times, and this is how you do it, I times, okay? So these are just a bunch of notions. For a single output system, x dot is fx with the output y is hx, then y dot is lfh, y double dot is lf2h, and so on and so forth. If v is a Lyapunov function, okay, this is a recollection of what we used to do when we were talking Lyapunov stability, okay? So we use this notion of LFH, LFV. Now, another important notion is the Lie bracket of two vector fields f and g. The Lie bracket is also a vector field with this definition. Lie bracket of f and g is nabla gf minus nabla fg, where f and g are two vector fields on Rn. The Lie bracket of G is also written as adjoint with G of G with respect to F, is the adjoint of G with respect to F. And why is this done? So we can easily write Lie bracket I times, okay? So this is the Lie bracket of between F and add F I minus 1 G for I1 and so on. Now we consider we have an example. We consider this simple input this simple nonlinear system where f is this and g is this. The Lie bracket is this one. It's also a vector field, as you can see. And now we have some properties that we discussed also. We also discussed last time. Bilinearity. You see how when you do the Lie bracket of an addition of two vector fields with respect to a third vector field is this formula. So, like I said, this is called bilinearity. Okay, and it can happen in both left and right terms. Okay, skew symmetry, skew commutativity. Okay, it's skew. So Lie bracket of f and g. You remember we proved these properties last time. So here I'm just going to recall them. And that's all. Lie bracket of f and g is minus Lie bracket between g and f, and the so-called Jacobi identity. So the Lie derivative of h with respect to the adjoint of g with respect to f is LF LGH minus LG LFH. So these are the main properties of the Lie bracket. Another important notion is the so-called notion of diffeomorphism. Okay, this is used to be able to compute coordinate transformations. Coordinate transformations are essentially diffeomorphisms. Diffeomorphism is adding something else to a mapping besides differentiability, and that's the existence of an inverse function. So a function phi defined in a region omega is called a diffeomorphism if it's smooth and if its inverse phi inverse exists and is smooth. Okay. In the region omega, in the whole space Rn, if the region omega of the whole space Rn, then phi x is a global diffeomorphism. Global diffeomorphisms are rare, it says here. We are looking for local diffeomorphisms. Okay. And usually the coordinate transformations are local diffeomorphisms. Let phi be a smooth function defined in a region omega in Rn. If the Jacobian matrix nabla phi is non-singular at some point, then phi x defines a local diffeomorphism in a subregion of omega. Okay, so locally, if the Jacobian is invertible, then indeed that function locally is a that vector field locally is a diffeomorphism. Okay, so now here it shows you how to apply diffeomorphism, right, leading to coordinate transformations. Okay, coordinate transformations. Okay, you have the dynamical system described by this function. You have a new set of states, and this is how you apply a coordinate transformation in the new set of states. Okay, and here they just forgot to mention x is in phi inverse of z, because you need to write everything in phi inverse of z. Okay, and in the new representation, you have this of the system. The system is the same, but with a new state-space representation in the coordinates z, and x is phi inverse of z. And here is an example of a non-global diffeomorphism. For instance, this one. This is the Jacobian. Okay, with rank 2 at x00. This is a local diffeomorphism around the origin. Okay. In the set omega, where because you have sine x2, where the absolute value of x2 is less than half pi. Okay, outside this region, the inverse of phi does not uniquely exist. That's the idea. Okay, outside this area because of the cosine appearing here. Okay, this is a local diffeomorphism. We also have the theorem of Frobenius. This is an important tool for feedback linearization, provides a necessary and sufficient condition for the solvability of PDEs, because you need PDEs. Consider a PDE with n equal to 3, which is this one, where fi, gi are known scalar functions and h is an unknown function. The set of PDEs is uniquely determined by the two vectors f and g. If the solution h exists, then the set of vector fields f and g is completely integrable. When are these equations solvable? That's the question. And the Frobenius theorem is answering this question for this system of partial differential equations. Okay, so the Frobenius theorem states that the equation 7 has a solution if and only if there exists scalar function such that the Lie bracket between f and g has this linear property. Okay, is expressed as a linear, can be expressed as a linear combination of the vector fields f and g. Okay, this condition is called the involutivity of the vector fields f and g. We discussed this last time. Okay, geometrically it means that the vector field Lie bracket between f and g is in the plane formed by the vectors f and g. The set of vector fields is completely integrable if and only if it is involutive. Okay, so involutivity is a very important, and we're also going to discuss about distributions. Okay, and here we have the definition of complete integrability. A linearly independent set of vector fields is said to be completely integrable if and only if there exists n minus m scalar functions satisfying this system of PDEs. Okay, so it's very useful. Number of vectors m, dimension of the vector n, okay, and the number of PDEs is m times n minus n. Definition of involutivity: a linearly independent set of vector fields is said to be involutive if and only if there exist scalar functions like this. The Lie bracket of any two vector fields from the set is a linear combination of the vectors of the set. Okay, and it's also a member of the set. Constant vector fields are involutive since their Lie brackets are 0. That makes sense, because you have derivatives and the derivatives of constants are 0. A set composed of a single vector is involutive also. Involutivity means that the rank of f1 up to fmx, if you put them together, of this matrix, okay, is also, it equals the rank of f1 up to fm with an addition of the Lie bracket between any two vector fields fi and fj for all x and all I and j. And the theorem of Frobenius, stating that if you have f1 up to fm, a set of linearly independent vector fields, the set is completely integrable if and only if it's involutive. And we have a set of PDEs, look here, two PDEs, okay? The associated vector fields are f1 and f2. f1 is this one and f2 is this one, okay? All right. Since f1 and the Lie bracket of f1 and f2 is this one, the set f1, f2 is involutive, just like the definition says, and the set of the PDEs are solvable. They are solvable, okay? Okay. And now we try to apply these notions to feedback linearization concepts and to integrate this into feedback linearization. So we have the following single input, single output nonlinear system. X dot is fx plus gxu, where f and g are smooth vector fields. Okay, this is an affine in the input system. Okay, I wouldn't say linear in the control because it doesn't generate linear combinations. If we deal with this class of systems, where W is an invertible scalar and phi is an arbitrary function, you can use V like this to get the form 8. Control design is based on V, and U can be obtained inverting W. W, sorry, W. Okay. Okay. So we are looking for conditions for system linearizability and for input state transformation. We need to compute the transformation, and we need a method to design controller based on such a linearization thing. So these are the three objectives we are trying to follow now. Input to state linearization. The nonlinear system A to F and G are smooth vector fields is input state linearizable if there exists a region omega in Rn and a diffeomorphism phi and the control law U is alpha x plus beta x v such that the new state variable z equal phi x and the new input variable v satisfy this linear time invariant system. The new state z is called the linearizing state, and the new state control law u is called the linearizing control input. Z is z of x actually. Okay, is a coordinate transformation. Okay. Look at number 9. This is in controller canonical form. Look here at the shape of A and B. So this is in controller canonical form. This linear companion form can be obtained from any linear controllable system by a transformation if U leads to a linear system. So if U is linearizing, then you can easily bring any linear system to controller canonical form. This is a special case of input-output linearization leading to relative degree R equal to n because you have no zeros. Hence, if the system is input-output linearizable R equal to n, it is also input-to-state linearizable. On the other hand, if the system is input-to-state linearizable, it is also input-to-output linearizable with the output y equal the state z and the relative degree R equal to n. Okay. Input-to-state linearization. An nth-order nonlinear system is input-to-state linearizable if and only if there exists a scalar function z1x for which the system is input-output linearizable with the relative degree R equal to the dimension of the system n. Okay? This lemma is qualitative, is not quantitative. We can't compute the coordinate transformation. We can neither compute the coordinate transformation nor the controller. Okay. Conditions for input-to-state linearization. The nonlinear system 8 with the vector fields f and g being smooth vector fields is input-to-state linearizable. Okay, now this is a theorem to characterize the definition. If and only if there exists a region omega such that the following conditions hold. The vector fields, look, you have a lot of Lie derivatives here, are linearly independent in omega, and this set is involutive in omega. This is, in the linear case, this is related to the property of controllability. So essentially it says here that the nonlinear system is input-to-state linearizable if and only if it's in some way controllable. So, okay. So the first condition can be interpreted as a controllability condition, okay. For a linear system, the vector field above, I mean this guy, becomes this. You can try to do this as a homework. Okay, try to apply these conditions to a linear system ABC. Okay, and the linear independence in the second condition is equivalent to the invertibility of the controllability matrix because this is a single input, single output system, and the controllability matrix is square. Okay. All right. Essentially, these and this in the linear case are equivalent. The first and the third condition are equivalent in the linear case. The second condition is always satisfied for linear systems since the vector fields are constant. Makes sense. But for nonlinear systems, this is not necessarily satisfied. So the linear case is a particular case with constant vector field. Okay, it is necessary according to Frobenius theorem for the existence of Z1x. If Z(x) is a smooth vector field in omega, then the set of equations that the lead derivative of Z with respect to G and so on is 0 is equivalent to this condition. Okay. Right. We don't talk about the proofs. We just skip the proofs. Now, here is, once the proof is over, the proof is constructive in some sense because it shows you how to get the condition. But we are going to skip the proof because we saw this a little bit last time. And we're going to get to the main result. So how do you do input to state linearization? You construct these vector fields, okay, using Lie brackets. You check the controllability and the involutivity conditions with the Lie brackets and the sets, the rank condition. If these conditions hold, you get the first state Z1 from solving this system. You compute the state transformation of this form. This is how you pick Z, and the input transformation with alpha and beta like this. And this is the linearizing input. Okay, this is the linearizing input. And now we have the example of a single link flexible joint manipulator connected to a motor via the shaft or torque. Okay, this is technical stuff. We have these equations of motion, as you can see here. These are rotation motion equations, second principle. Okay. So we have the equation nicely written here. The nonlinearities appear in the first equation and the torque is in the second equation. Okay, the input is in the second linear equation. You let X be like this. This is a mechanical system with two angular positions, so you have a fourth order mechanical system of this form. Look at G. G is of this form. Controllability and involutivity conditions, you just compute here the controllability matrix, sort of. Okay, so this is essentially the controllability matrix, okay, like a controllability matrix, okay, which is this one. And as we can see here, look, this looks like a controller canonical form because this is skew triangular. This is a skew triangular matrix. And the determinant of this, so this is invertible. This is invertible, okay? It's full rank for K positive and the product IJ finite. Yeah, of course. Okay. Vector fields are constant, so it's involutive. So the system is input to state linearizable according to the theorem. We compute Z. We need to compute Z. So Z1 is a function of X1 only. So Z1 equals X1, and then you get Z2, Z3, and Z4 to be of this form. This is the coordinate transformation. Check it out. Okay, so we have a good recipe. How to compute these things. The input transformation, alpha and beta. Okay, and as a result, what do you get in closed loop? You get this very simple system, and you also need to compute the inverse transformation, which is this one. So this is an example on how to apply the input to state linearization algorithm on a system. Okay. Note that the state and the input transformations are defined globally. In this example, the transformed state has a physical meaning. The transformed state has a physical meaning. The link position, Z1, Z2 is the link velocity, the Z3 is the link acceleration, and the Z4 is the link jerk. Very interesting. So we managed to get a physical meaning to these equations, which look just like in the beginning. Okay. Okay. It can also be obtained, it says here, through input-output linearization. If you differentiate the output Q1 4 times, it says here. We can transform the inequality 11 to a normalized equation by setting this guy being equal to 1. Okay, so you can do all sorts of manipulations, but the procedure is very clear. Control design we have now. So once the linearized dynamics is obtained, you get a tracking or so we can solve either a tracking or a stabilization problem, just like we mentioned earlier. Okay, if you take this guy Z1 differentiated 4 times equal to V, a tracking controller can be obtained like this. Take V like this. Okay, the error dynamics. This is a polynomial. This is a linear system. So these are polynomials. Okay, so you have to, this is exponentially stable if you pick this coefficient such that this polynomial is a Hurwitz polynomial, and you can do that. You can do that. You just use the Hurwitz criterion, and you get inequality-like conditions for the coefficients A1 up to A4. Now, we can also do input-output linearization. Look at this system. Input-output linearization yields a linear relationship between the output Y and the input V. Okay? How do you generate such a relation? What's the internal dynamics and the zero dynamics associated with this linearization? How to design a stable controller based on this technique? So these are the main questions. The basic approach is to differentiate the output until the input U appears. So you have to compute the relative degree, first of all, to be able to see the pole zero excess. Okay, sometimes the cancellation might not be possible due to the undefined relative degree. So sometimes you can have a problem. So you have to have a well-defined relative degree. Differentiate Y and express it in form of a Lie derivative, like this. You see LFH plus LGHU. If LGH is non-zero for some x equal to x0 in a neighborhood omega, then continuity implies that this is not zero in some neighborhood omega of x0. Then you can easily compute, you can do this relation and compute u from this first equation in this form. And this gets you a linear relationship between the output y and the input v, namely y dot equals to v. If, however, LGH is 0, then you'd have to differentiate once again. Okay? If you still get 0, you keep differentiating until R, until you get the relative degree, okay? To get the relative degree, until you get this relation for some x equal to x0. Okay? So you just keep differentiating the output until you see this relation occurring. Hence, you differentiate y r times, differentiate r or I r times, you get this relation between r differentiated r times and the input u. Look, it's showing up because you stopped with a relative degree. And this is the general control law you can pick to achieve this linear, this R integrator like, yeah, this is a chain of R integrators. That's what this equation tells us. You have a chain of R integrators. The number R of differentiation required for you to appear is called the relative degree of the system. We know that. Okay, if the relative degree equals the dimension of the system, then you can easily do input to state linearization with Z1 equal to Y. Okay, right. And now, in general, a single input, single output system is said to have a relative degree R if LGLF I times hx is 0 for I less than r minus 2, and LGLF r minus 1 hx is not 0, is not 0. Now, what is an undefined relative degree? We have to see the opposite. We have to see the bad apple this time, okay, to be able to understand everything. Right. Sometimes we're interested in the properties of a system about a specific operating point x0. Then we say the system has relative degree r at x0 if LGLF r minus 1 h x0 is not 0. However, it can also happen that this guy is 0, but non-zero in a close neighborhood of x0. So exactly in the point is 0, but then in the neighborhood is not 0. So the relative degree is not defined in this case at x0. An example is this system where ρ is a smooth nonlinear function. If you have the state x dot and let y equal to x, the system is in companion form with r equal to 2. However, if we define y to be x squared, so picking a different output, see, this relative degree stuff it depends on the output because the zeros depend on the output you choose. Then y dot is 2x dot, y double dot is this guy, and then LGLFH is 2x. The system has neither relative degree 1 nor 2 at x0 equal to 0. Sometimes a change of the out. So you have when this happens, okay, because for x equal to 0, they're all 0, you have to change the output, okay, to get the relative degree to be well defined. So this is very easy. You change the output, you measure something else. Okay. Normal forms, when the relative degree is defined as r less than or equal to n, using the output y and its derivatives up to r minus 1, we can transform the system into so-called normal form. A normal form allows a formal treatment of the notion of internal dynamics as 0. So we need a normal form to characterize the internal and the 0 dynamics. Okay. All right. So you define mu, this vector. The normal form is written in this form. Mu dot is mu2 up to mu r. But why mu2 and not mu1? Oh yeah, mu2 up to mu r. And then mu r plus 1 has this form with a and b and u. You still have a state psi. Yeah, psi dot is w of mu and psi, and the output y is mu1. The mu and the psi are called the normal coordinates or the normal states of the system. The first part of the normal form in 17 is another form of 15. However, in 18, the input u does not appear. 15, who's 15? This guy. This guy. But without u. The system can be transformed to this form if the state transformation phi is a local diffeomorphism. Makes sense. You have to have a coordinate transformation to achieve this form. To show that phi is a diffeomorphism, we must show that the Jacobian is invertible. That means that all of these guys are linearly independent. Okay. 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 Look, psi are obtained solving n minus r, so n minus relative degree PDE equations. Zero dynamics, system dynamics have two parts: external dynamics, mu dot, internal dynamics, mu dot, internal dynamics, psi dot, this guy. For tracking problems, y has to go to YD, one can easily design V once the linear relation is obtained, of course. That's why you do feedback linearization. Okay? To get a linear relation. Hold on a second. Yeah. The question is whether the internal dynamics remains bounded. Okay? Okay, no problem. But you can also talk to me. No problem. Where's this guy? Okay, so sorry about that. Where were we? Stability of the zero dynamics, internal dynamics in Y is kept to zero, gives an idea about the stability of the internal dynamics. That only makes sense. U is selected such that Y remains zero at all time. So if Y differentiated R times has this form and is equal to zero, then U0X has this shape. And in normal form, you get this. Yeah, you get this explicitly. So in the coordinates, in the new coordinates of the normal form, okay, you explicitly get relations 19. And you have this example, for instance, you have this example. Note that y dot is 2x2, y double dot is 2x2 dot, so it's twice this relation. The system has relative degree 2, because u appears when you differentiate twice. Okay, and then LFHX is 2x2, LGHX is 0, LFHX is 1. So you get the normal form to be you get mu1 like this, mu2 like this, and the third function, psi, is obtained solving this PDE with one solution, because PDEs are not easy to solve, but this is an easy PDE, so it can be solved with this solution for psi. With this solution for psi. Okay. Consider the Jacobian transformation. So you take this coordinate transformation with this Jacobian matrix, which is non-singular for any x, and with this inverse transformation. Okay, and this is the normal form you get. This is the normal form you get. The zero dynamics is obtained setting mu1 and mu2 equal to 0, and psi dot in this case is minus psi. Okay, so to get the zero dynamics is not necessary to put the state in normal form. Since mu is known, we can intuitively find n minus r vector to complete the transformation. As mentioned before, the zero dynamics is obtained by substituting u0 for u in the internal dynamics. A nonlinear system with asymptotically stable zero dynamics is called asymptotically minimum phase. We said that before. If the zero dynamics is stable for all x, the system is globally minimum phase, otherwise all the results are local. And now it shows you here how to achieve local asymptotic stabilization using feedback linearization. If you have a nonlinear affine in the input system 22, and if you assume that it is input-output linearized with this relation with relative degree r, and this control law to yield this mapping, now you choose V to have this form, and this polynomial needs to be Hurwitz. This polynomial needs to be Hurwitz. Okay. Okay. Then, provided that the zero dynamics is asymptotically stable, the control law 24 and 25 locally stabilize the whole system. And we have a result. Suppose that the nonlinear system 22 has a well-defined relative degree R, and its associated zero dynamics is locally asymptotically stable. Now, if Kr are selected such that Ks is Hurwitz, then the control law 24 and 25, it's a locally asymptotically stable system. Okay? So we have a nice result. And you have the proof here. You have the proof here, which we are going to skip. Okay? Zero dimension, its linearization. Psi dot is A type. Psi is either asymptotically stable or marginally stable. If A2 is asymptotically stable, then all the eigenvalues of the above system are in the left half plane and the linear. Okay. Now this is interesting. The above stabilization method can treat systems whose linearizations contain uncontrollable but marginally stable modes. Very interesting. While linear control methods requires the linearized system to be strictly stabilizable. Okay. So in general, when you do Kalman filtering, you need your system to be stabilizable. That means that all the uncontrollable modes of the system need to be stable. Whereas in this case, apparently, in this nonlinear theory, you do not need that. You do not need full stability or asymptotic stability of the uncontrollable modes, but they can also be marginally stable. So probably, say, close to the imaginary axis, or even probably on the imaginary axis, which was not possible in the linear theory. For stabilization where state convergence is required, we can freely choose an output to make zero dynamics asymptotically stable. So we can always change the output y. And we have another example here of a nonlinear system, linearized in 0. It's uncontrollable, you see. However, if you get this output, you can do relative degree 1 with the zero dynamics x1 dot is minus 2x1 to the power 3. The zero dynamics is asymptotically stable, and so the control law locally stabilizes the system. You can also achieve global asymptotic stabilization. Stability of the zero dynamics only guarantees local stability unless the relative degree is n, in which case there is no internal dynamics, like we mentioned before. Can the idea of input-output linearization be used for global stabilization problem is a question. Can the idea of input-output linearization be used for systems with unstable zero dynamics? So, non-minimum phase. Global stabilization approach based on partial feedback linearization, so we can also do that, is to get the problem as a standard Lyapunov controller design problem. So this is also an application of Lyapunov stability. But simplified by the fact in normal form, part of the system dynamics is nonlinear. So the basic idea is to view mu as the input to the internal dynamics and psi as the output. And this is, it tells you how to achieve global asymptotic stabilization, and here is an example of it. Okay? Very interesting. You have to check this out. Okay, and here it shows you the example of a non-minimum phase system that can be stabilized. Okay. And finally, there is a discussion about tracking control. So if you want to achieve not only stabilization, but also tracking, you can do this with feedback linearization. Very nice. Okay, very nice. Okay. Of course, using the normal form and everything like that. Okay, and this is the command number 27, equation 27, describes the tracking control. The tracking control. Okay, there are some papers, Christopher Burns and Alberto Isidori. Christopher Burns, I think, is dead. Alberto Isidori is old and alive in Italy. He has a famous book of nonlinear control system, dynamical systems, and there are a lot of proofs there, and he invented all these ideas. Okay. You can also do tracking control for non-minimum phase systems. Okay. Yeah. Essentially, you change the output a little bit to achieve that. If it's non-minimum phase, very interesting. Okay. Right. So this is pretty much all I had to say throughout this lecture. If you have any questions or remarks, please talk to me about it right now. I'm listening. Questions or remarks?
Will this presentation part of the exam?
Can you repeat that, because I didn't hear you properly?
Sorry. Will this presentation right now be part of the final exam? So do we have to study it in detail, or?
No, you just need to understand the things properly and do your assignments. The final examination is you have papers. You gave me a document with the assignments you took for the final exam. Essentially, you study a paper and you present the paper and do the simulations, right? So you don't need to do it in detail. You have to use it if you need it. Okay. If you need this in in the paper study you choose, you can read it in detail. Okay. I'm trying to open the document Andrei shared with me to see what papers you picked for the final exam. There is a document on the main channel of the, okay? A research paper for the exam. Who is Andrei Beshlaga chose project 3. Okay, you have to pick a paper. There is a document. Okay. This is for autonomous agents. This is not for.
No, there are more pages.
Control of complex nonlinear control. Oh, you have it here. Oh, I'm currently checking which topic suits me the best. Is written here.
I didn't finish that. That's why. Okay.
No problem. You still have time, but please start. Please. You have 2 weeks left to decide. I think this is more than enough. You have to make a choice. Okay? You have to make a choice. This is a.
Have any recommendation of the remaining papers? Maybe which is like a little.
It's up to you. I can't recommend anything. Sorry.
Okay.
you pick it up.
Not any.
You pick up whatever. Okay, if you find something else, you can also show me something else. But I think these papers cover most of the topics covered, most of the topics discussed in this lecture. So you pick a paper, you see. For instance, Andrei picked number 5, Radu picked number 1, Teodor Badea picked one of my papers, number 8, and you have to pick whatever you like. I don't want to influence you, okay?
Yeah, I was just not sure if I should like take a paper which is like short, like based on the fact that it might be easier to implement it, but it might also be harder because there is less description how it's done. So I was not sure. That's why I didn't.
If you're not sure, you can pick 2 papers. I don't mind. You can present more.
But that's increasing the workload. So I won't go.
I know. It's more work. But it's up to you. Again, I can't influence you. I can't tell you what to pick. You know, it's your decision.
So we will then do a final presentation on that?
Yes,
or?
yes, because you pick an exam date and you come and do a presentation and run the simulations, show me the simulations, the software you designed. And in the presentation, you have to show me what you understood and what's your view on the paper. Maybe you don't like something, maybe you like something, maybe, I don't know, you find a mistake or you find an improvement. It's research, so you have to show me that you did research on that paper. This is a research master and this is a research course, lecture, course, yeah, topic. So you see what I mean?
Yes, of course.
I think you can do it, no problem. Right. Anyone else? Any other issues? Any other issues? Well, if you have questions, you can ask me next week, okay? For me, from my side, there's nothing more I need to present to you. So it's kind of, that's all, folks. Okay? So the lecture is over, essentially. So now, if you have questions, discussions, okay, we can talk about it next week and the week after that. We have 2 more lectures left. So if you want to meet and discuss anything you're interested in regarding this lecture or anything else related to this master or to the studies or whatever, we can discuss. Okay? You agree?
Yes.
Okay. Right.